as we start moving into the next few chapters in this class, we're going to be looking at systems that are in multiple dimensions. And when we have things in multiple dimensions, we often care about directions and as well as just quantities. And so we're going to do a brief review of vectors. Hopefully this is familiar material, but this is Math Chapter C in the textbook. And so as we start looking at things like the rigid rotator in chapter 5, and as we start looking at angular momentum, a property we'll start considering for things that are spinning, particularly electrons, vectors become an important mathematical concept. And so a vector, just to review what a vector is, it is a quantity with both a direction as well as a magnitude. So things like force that you learned about in physics, they push in a particular direction. They have a specific strength, right? If we think about how strong a force is, so think as something like velocity, force, and as we'll see, angular momentum is another vector quantity that we'll see. And so the way we represent vectors often is with an arrow, right? So the direction represents our direction, and then the length of the arrow represents the magnitude. Now, how do we work with vectors? So one of the important things that we need to do with vectors often is add them. And so we represent vectors as, say, a letter with an arrow over the top of it like this. So this would be our vector A. And if we have, say, another vector B, we can find the result of adding those two vectors C. And we do this by placing the start of B at the end of A. So if I draw a picture here, so if we represent a vector, say, on a xy axis, if we have, say, our vector A here, and another vector B, our vector C will be from the start of A to the end of B. So A is here, B is here, and C is here. And vector addition does commute, so A plus B is the same as if we do it in the other order, B plus A. You'll get the same resulting vector C from either one of those. If we do subtraction, so if we say want to do A minus B, and we can get some final product C from there. What we do is that we draw the negative vector. So we draw, in this case, B in the opposite direction. So again, if we represent our vectors here on an xy axis, if we say A is roughly the same, we would draw B in the opposite direction, and so our resulting vector C, let me label all these, A, B, C, will be down here instead, so it'll be shorter. And so that's how we represent this. Now, it's usually not practical to always draw out our vectors explicitly like this. And so what we often do is we'll take our vector, say A, and say we're representing this in 3 dimensions, x, y, and z dimensions. So say this is a vector representing something happening in this room or something, right, where we have 3 dimensions to worry about. We can break down our vector into its components along each of those directions. So we can say there's the magnitude in the x direction times I here. I here is a unit vector, so a vector that's 1 unit of whatever units we're dealing with. It's a unit vector along the x-axis, and we'll have j and k. So these are just the letters that are traditionally used to represent these. J is along the y-axis, k is along the z-axis. So we'll have the magnitude of A along the y-axis times the j unit vector, and the same for the z-axis. We'll have the k unit vector. And this allows us to kind of represent our vector in a little bit easier way. We'll often leave off the unit vectors explicitly, but just kind of ax comma ay comma az to represent our vector. And this gives us a different way to add vectors. So to add vectors, we can take these components along each of the axes that we're considering. So if we have, say, a plus b, what we can do is just add up the components along each axis times their unit vectors. And that will give us our final vector. Okay, so that's a different way to do addition. All right, so I'll end this video here. We have a couple more vector operations that we'll look at in the next video.